Good morning, everybody. Welcome to the last week of school. This is it, the final week. You guys are all excited. A big lesson today on momentum. It's the second part of Newton's third law of motion. It's a little more complicated. We're going to take a little bit of time of some good examples for you on momentum and the law of conservation of momentum. Just a quick reminder, get the work in that's missing. If you have any work missing, please get it in so we can get it graded in a progress book and wrap up your year. Be done with it. Today you've got a easy review sheet to do on Chapter 2, Section 4, and then Wednesday is a chapter test, but it's going to be just on Chapter 2, Section 1, 2, 3, and 4. And multiple choice, so pretty straightforward test. I think you guys can handle it well, and that'll be it. I got some other videos to talk about on Thursday and Friday, some other stuff I'm going to be doing, and that'll be it. That'll be a wrap. So let's get right into it. I'll bring over the magic screen. Well, before we do that, first we're talking about Newton's third law. For every action force, there's an equal and opposite reaction force. Okay. I'm sitting on this chair, right? Gravity's pulling me down with an equal and opposite force. The Earth is pushing up on me. Okay. When you kick a soccer ball, your foot applies force to the ball also applies force to you. Why does the ball move away from you? Why don't you and the ball move in opposite directions equally? Because of your mass. You have a lot more mass than that ball. Excuse me. And so you are able to propel the ball forward, even though equal and opposite forces are pushing on each other. That's going to lead into the law of conservation of momentum. Momentum involves objects that are in contact with each other, hitting each other. Okay? So, here's your formula for momentum. Mass times velocity, which you've already read this, and maybe you already did a review, I don't know yet, but you did the reading. If you have a mass, something with a mass of 500 kilograms, a motorcycle or something, small, it's a couple of thousand pounds, or a little less. And you have a velocity, V for velocity of 20 meters per second, you simply multiply mass times velocity. Kilograms is mass, meters per second is velocity, or speed. You want to think about it that way? So momentum equals 500 kilograms times 20 meters per second gives you a momentum of 10,000 kilograms times meters per second. They don't have a fancy label for that, like newtons or pounds or anything. It's just kilograms times meters per second, which is what you're doing here, kilograms times meters per second. Okay? All right, so far so good. Clear as mud. So, which one has more momentum? Semi-truck or the car? That's a trick question. Think about it. Think about what you need to know. Mass times velocity. Okay? Well, we know that the truck obviously is going to have more mass than the car. But what about velocity? To me, it looks like they're both parked. Okay, you do need to know the velocity. If their velocity is zero, okay, if this is zero here, for instance, 500 kilograms times zero gives you zero. You would have no momentum. Okay, so if something is not moving, it has no momentum. So you need to know the speed. Could the car have the same momentum as the semi-truck? Yes. Theoretically, if the truck is moving really, really slow and the car is going super fast, you could reach a point where the momentum would be equal, or the car could even have more momentum than that truck. Okay? Back to Newton's first law, which has more inertia, this truck or the car. Now with inertia, it doesn't matter, again, if that's my alarm, got a meeting coming up. Which one has more inertia? Inertia is based on mass only. It's only mass for inertia. So it doesn't matter if it's moving or not. This truck will always have more inertia. Remember, inertia is a tendency for an object to resist a change in motion. So if it's stopped, it wants to stay stopped. It's going to be hard to get that truck going. If it's moving, it's going to be hard to slow down and stop because it has a lot of mass. Okay? Car's the opposite, not much inertia, therefore it means it doesn't have much mass. It's not going to take much energy to get it moving compared to the truck, and it's going to be able to stop a lot quicker than that truck. Remember my example? Watch when you're pulling out. Don't always give the semi-truck enough room because they can't slow down and stop if you pull out in front of them suddenly. All right, so take a look at this picture. You've got a bowling ball and a feather. Which has more momentum if these are in free fall? Think back to free fall. For these two to be in free fall, the only force acting on them is gravity. So this is in a vacuum. There's no air resistance. So since it's in free fall, what could you tell me about the speed of these two? They're the same. If they're dropped at the same moment, they're going to accelerate towards the earth at the same rate. They're both traveling at the exact same speed. So if their velocity is the same and their mass is different, that's the only change there. Obviously, which one has more momentum if they're going the same speed? Which one would you rather be hit by? Because it has less momentum. The feather, right? Because of its mass only. I should say, velocity is the same on these two objects because they're in free fall. So a feather's going to have less momentum than the bowling ball. Okay, law of conservation of momentum states that the total momentum, mass times velocity, of objects that interact remains the same. So you're out here bowling. The pins are stationary at the end of the alley, and like that. Pins are stationary at the end of the alley. You put the ball in motion. The bowling ball is the only thing that has any kind of momentum because it's in motion traveling down the alley. The pins have no momentum. What happens to the velocity when the velocity of the ball at impact? Okay. Keep in mind, the total momentum of objects that interact remains the same. So the bowling ball has a certain amount of momentum. It has a certain amount of mass, and a certain 5 kilograms, let's say, and has a certain amount of speed, of velocity, say whatever, 5 meters per second or something. The pins have 0 momentum. So the law of conservation of momentum states that on impact, what's going to happen to the momentum of the bowling ball? Is it going to gain or lose momentum when it hits those pins? It's going to lose momentum because what's changing on the bowling ball? Is the mass changing when the ball hits the pins? No, the bowling ball has the same mass. What happens to the speed of the ball? It's going to go down. So the bowling ball is going to lose some speed. Where does that velocity go to, that momentum go to? It's transferred into the pins. Remember, the pins over here have no momentum. On impact, the pins speed up, they start moving, and the bowling ball slows down. But that momentum, this law of conservation of momentum, that momentum is transferred. Same thing happens when you're breaking a rack of pool balls. Okay, the cue ball traveling towards the rack of pool balls has a lot of momentum. The rack of 15 balls at the other end of the table have 0 momentum until the cue ball hits them. Then the pool balls start to move. They gain momentum because they gain speed, and the cue ball loses momentum. It slows down just like the bowling ball. Okay. You've seen this in the Olympics. If you looked when they're talking about the Olympic friction, this is curling. These stones are slid down the ice into other stones and try to get into the bullseye. Well, defensively, you want to try to knock the other stones out of the way. So on impact, one stone will hit another, lose momentum, and the other stone that was impacted will gain momentum. It'll start moving. This one will, let's say this red one hits the yellow one. The red one on impact slows down or maybe even stops, and the yellow one starts moving, and then friction causes it to slow down. All right, I'm going to attempt something here. I'm going to attempt to take the show on the road to the other side of my room here. All right, I've got an air hockey table set up. All right, I've got some, I don't know if I can do this. Let's see, without too much damage to my basement. Yeah, let's go up there. So I've got a group of, this is difficult, a group of air hockey pucks, and I've got the paddle here. I'm going to give the paddle some momentum. I'm going to slide it. The pucks sitting in the middle have no momentum, but watch on impact when I slide the paddle into the pucks. Watch what happens to the paddle, the momentum of the paddle. It's going to lose velocity. It's not going to lose mass unless I break it. And this group of pucks over here is going to gain momentum. They're going to start moving. Right now, they have no momentum, 0. Do they have inertia? Yes, because they have a certain amount of mass, but they have no momentum. All right, here we go. This is going to be a good one. I'm probably going to miss. And let's try that again, because I know it was off screen. All right, that might work. All right, one more time. 1, 2, 3. All right, yeah, I know you guys are enjoying that. All right, here we go again. 1, 2. Got that. That one puck has momentum. It won't stop moving. All right, here we go. All right, 1, 2, 3. Some started moving, others didn't. Let's do it again because that was terrible. I want to smash them. 1, 2, 3. Keep laughing. Only gets funnier. All right, 1, 2, 3. This is terrible. You should try videotaping and playing air hockey. 2, 3. One more time. I'm going to do it right-handed this time. All right. 1, 2, 3. There we go. That was better. So the total amount of momentum was transferred. The paddle stopped relatively short in a short amount of time because it was losing speed and losing momentum. And the little pucks gained momentum, and then they lost momentum because of the friction. Okay, between the table. I know it's an air hockey table. It shouldn't be any friction, but there is a little bit of. It's not going to continue on forever. All right, let's see if we can get back on track here. All right, we're having a good old time with this. All right. Next thing, I've got, this is called, down here, Newton's cradle. I'm going to put a version of that up on the screen. Newton's cradle. I hope you guys can see that all right. Coming in okay. All right, I'm going to put it into motion. You guys have probably seen these around. Now, this ain't, it's a Newtonian demonstrator is what it's called, but you can demonstrate all of Newton's laws with this thing. All right, so you got object at, stop it. I'm trying to get it to go to rest. There we go. Objects at rest remain at rest, okay, unless acted upon by an unbalanced force. Objects in motion remain in motion at a constant velocity and in a straight line unless acted upon by an unbalanced force. So that's the first law, okay? Now it's in motion. There's a couple of forces acting on it. Unbalanced force has got gravity pulling down on it, bringing it back to center, okay? And it's not moving in a straight line because the wire's attached. It's causing it to go in a kind of in a curve. If you extend this all the way out here, whoops, it's kind of going in a curve. So, got some unbalanced force. And then this, you got, eventually this thing will slow down and stop. Not going to go on forever, even though it's computer. It's actually losing energy. Some of that energy is being transferred. Actually, all the energy is never lost. Okay, as it loses speed, that's being transferred into a little bit of heat energy right here on impact. So it's losing some energy here, and everything's being brought back down to center. Okay, so you can see it's getting smaller and smaller. And then the second law, you got force equals mass times acceleration. You can increase the mass and increase the mass again. If I apply the same amount of force, if I lift it to the same point, okay, and if I'm using less mass, it will accelerate quicker. If I'm using a lot more mass, it can accelerate there. And of course, Newton's third law, action, reaction, whatever. Let's grab one of these. Okay, action force, reaction force. I have the mass of one ball in and one going out. Okay, equal and opposite actions, action force, reaction force, and I can go 2 in and 2 out. The mass of 2 balls in and 2 out. 3, same thing, 3 in, 3 out. And we can do 4. Hopefully you guys can see that okay. And then, amazingly, 5. Look at that. Okay, last thing, guys. In your book, they have some examples of these collisions with these little train cars. Okay, they give you the mass. The blue one has a mass of 2 kilograms, and it's traveling 4 meters per second. So its momentum would be 2 kilograms times 4 meters per second, which gives you a momentum of 8. Okay. Now, both cars are moving. This car is moving slower. The green one's moving 2 meters per second, and it has the same mass, though, of 2 kilograms, same as the blue car. So it has a momentum of only 4. So it's moving, has less momentum. So the blue car collides with the green car, and look what happens on impact. It's not going. The blue car is not going to lose mass. It's going to lose speed. It's losing some momentum. It's down to 4 meters per second, and the green car accelerated to. It's down to 2 meters per second. The green car accelerated to 4. So this speed was transferred. Okay, this one hit this moving vehicle from behind. This one lost momentum. This one gained momentum. Went from 4 to 2. This one went from 2 to 4. In a car situation, maybe you're driving down the road and somebody is not paying attention, they're texting or whatever, and they rear end you, they hit you from behind. They lose some speed, you gain some speed. Okay, they lose momentum, you gain momentum, and some of that energy may be transferred to you as the driver. And certainly, don't want you to be injured. You've got to watch out all around you when you're driving for other cars who may be coming up behind you and may hit you. That happened to me a few years ago. I was getting ready to turn, make a left-hand turn, and a guy wasn't paying attention and slammed into the back of me, shoved me into the other lane. I gained speed and he lost speed on a collision. Fortunately, nobody was injured. All right, the second example in the book. collisions with one moving object. Okay. So the blue car is moving 4 meters per second, 2 kilograms, 4 meters per second. The green one is stopped at a red light. Okay. Kind of like I was stopped in the road. I was dead stop, waiting to turn left. I was stopped. This guy collided with me. This blue car collides with the green one, loses its speed, which means it loses its momentum, and that energy, that momentum, is transferred to the green one. It's smashed into this one. This one started moving. This happens every once in a while too. You got to, when you're stopped at a red light, watch out for the guy coming up behind you. Is he or she paying attention? Are they going to stop at that red light? When I saw the guy approaching me at a high speed, I knew he wasn't going to stop. I did take my foot off the brake and put it on the accelerator to try to get out of the way. Didn't work. I didn't go fast enough, and he slammed into the back of me. So, again, watch out for people behind you and what they're doing. And the last one is two connected objects. Okay. Here we go. Same blue car, 4 meters per second. This one is moving 0, the green one, and they couple. Okay, even though they're on impact, the trains couple and link together, and they're both traveling. This one loses speed, loses momentum. The blue one, the green one gains speed, gains a little momentum, and they both end up moving down the track at a combined 2 meters per second. Okay, and the momentum is the same, 8 kilograms times meters per second. All right. So I'll leave you with that. That is, sorry about that big headshot, is all I have for today. Law of conservation of momentum, the second part of Newton's third law, that at impact, certain objects will, the objects will lose momentum, and other objects will gain momentum in the form of speed, typically, in the form of mass. That's it. So one more video to go, one more week, and we are done. So hopefully everybody's well and working hard. Get that work in as soon as you can, so I can get it graded in the grade book. And that's it. Nice seeing you.